Yes, we're going to be talking about a process for virtual sensing development, specifically for indoor air quality monitoring in democratized manufacturing environments. Some of you may think, okay, what's a democratized manufacturing environment had to do with built environment or even with construction? So these environments, the makers, they use additive manufacturing technologies like 3D printing in spaces that are not necessarily ready for that kind of process, and they normally work on a budget. So the spaces that they normally use would be like offices, meeting rooms, labs, and even at home. And why this may become concerning, so to start with, you may detect some unusual thing like bad odors, dust or particles, or even the feeling of pollution indoors. So to explain this, we are not going to only follow the path of a maker in this kind of environment, but also the path of just a data scientist in a normal office environment, so we can see how would that be applicable in a normal space. So I'll run a little bit faster than expected with the context because of the limitation of time, but long story short, both Noah and Mikey, they found out that there's some problems in their spaces. In an office could be from lack of cleaning or the use of strong cleaning products or just the outdoors. And since they are also researchers, by looking in the literature, they found about the most dangerous pollution or pollutants in the space. So for instance, particulate matter, oxides, volatile organic compounds, and so on, and the impact on health as well. So for Noah in this case, he found out that the exposure to these chemicals can be correlated to breast cancer and reproductive hazards. And for Mikey, the process that he runs, it can lead to brain strokes, it can lead to chronic pulmonary diseases, lung cancer, and so on. So they kind of feel like, oh my God, we are going to die, even though we are in a supposedly safe space. And they quickly go into what can we do to figure out what's in the space, what's the current situation of the pollutants. They quickly discard the high-end equipment because, as we said, they are on a budget and they cannot really afford this high-end equipment. Also because even that this kind of equipment is accurate, it can only do like one-off samplings, and then they need to rely on other alternatives like low-cost sensors. The problem with the low-cost sensors is that they are normally not so much accurate, and they need further calibration to proper do estimations on the pollution found in the space. So for that, some authors already have some signal processing, and they embed this into a piece of software which is called virtual sensor. And basically they come from other piece of research which is related to software sensors, which is an online instrument for measure or that supplement the normal monitoring that we would achieve with local sensors, always using these hardware sensors as a reference to provide real-time estimations. To summarize, these are the two main categories of virtual sensors present in the literature. Ones are for extending the capabilities of hardware sensors. The other one is just to reduce the number of sensors required, or maybe to do some remote sensing and in target spaces or locations that are not accessible. So they both found so many techniques and so many processes to follow, and they kind of think, all right, where to start to build up a virtual sensor. That's where we come in and provide this process. It's mainly based on 4 different stages: one for the hardware sensor deployment that you may be familiar with, the other one for data collection to characterize the pollutants in the space, and finally the virtual sensing design itself, and the always ignored deployment in a standalone system. So in this case, the 2 sub-steps, if you like, on sensor deployment is sensor selection, the calibration of that against the source of truth, and the sensor positioning itself. in the target space to highlight basically these two researchers found about the potential pollutants in the space, and therefore that informed the decision of the sensor selection. Obviously, they needed to discard this high-end equipment, as we said, and they had to trust on the manufacturer calibration. And for sensor positioning, they needed to do this in a sort of an informed way. So since Noah in the office space, she wasn't so sure of the process happening there, because just the normal office is an uncontrolled environment. She just positioned the sensors around her desk, and she used IFC to record the sensor position. She's a little bit proficient with this, and she used the IFC sensor and IFC asset classes to do this. And Mikey, he had some source of the pollution, which is the 3D printers themselves, so he could position the sensors around them. For data collection and characterizing the pollutants, you may be also familiar with this. You need to select your variables, design some experiments, and then analyze your data. We've seen some examples in this session already, so I won't spend too much on that. But basically, the purpose of NOAA was to find about concentration, and the purpose of Mikey was about the dispersion in this cabinet that we've seen, just to figure out about some details of the experiment. NOAA had to consider different times of the day and consider recording manually non-controllable situations like windows and doors that are open, ventilation, and occupancy. And for Mikey, he needed to start with the same conditions, repeat the experiments for validation, and also avoid the occupancy during the experiments because of the impact on safety, and they can also have an impact on measurements, because he found out that CO2 can pollute their estimations in PM. So yeah, after some data analysis, they discovered first of all the spikes upon window openings and in presence of airflow. And for Mikey, he just discovered or kind of characterized the process on when the pollution comes up and when it decays, which could even be after the end of the printing job. That could inform things like when to open the window of the cabinet to access the structure. So again, the third step is the virtual sensing design. So this kind of follows the same path of any data scientist, any machine learning engineer. So again, I won't spend too much time on it, just to highlight that they both wanted to reduce the number of sensors. And in the case of Mikey, he also needed like increased or reduced downtime on the sensors that may fail because of power, because of network drops and things like that. Remember that we need a real-time monitoring in these cases. For model selection, one thing that they both discover is that these models are not necessarily transferable into other spaces unless there's some physical connection and the pollutants can filter between these two spaces. The rest of it is kind of quite standard, but the kind of results that they've got using, in the case of NOAA, linear models and certain feature selection, and in the case of Mikey, using non-linear models like a booster tree, and it was certain. But just to remind you, this is always an iterative process of trial and error, and we need to rerun this until we find the model that we are kind of happy with and it's accurate enough for our target space. The important bit kind of comes here. We need to, once you have like a beautiful model that you think it's going to be accurate for your space, and you can start using it, but just the model itself is not enough. You need to build this onto a system that behaves directly like in any other hardware sensor. So if anyone comes in and see the data, he wouldn't even notice if it's a virtual or a hardware sensor. And for that, there's some literature that attacks this and kind of creates an architecture for using the virtual sensors seamlessly. You need evaluation of these sensors and also long-term calibrations, because again we need to think about them like any other hardware sensor, and basically you can use other hardware sensors in the space as a reference to this calibration. So that transition shouldn't have happened, but anyway, this is the standard process summary. Again, the goal of it is kind of to guide practitioners and researchers to enhance the the awareness on indoor air quality at a low cost. So, as conclusions, we found that indoor air quality monitoring in general is not sufficiently explored, and we think that for the available literature, it can have the potential to inform materials and design of indoor spaces, as well as maintenance during the operation phase of the built environment. We followed a couple of cases to explain the process, and we also found some limitations that I think is interesting to address in this forum. Well, first of all, obviously we need to find similar spaces to validate the models that we found, and the approach to kind of cover more casuistic in the process and kind of enhance it. And we need to overcome that lack of trust in low-cost monitoring through evaluation and calibration in the field, not from the manufacturers. And something interesting as well is that the case of NOAA and non-characterizable sources of pollution can be hard to find out. How about other phases in the building in construction? Can we use maybe wearable sensors that the workers can use to then inform virtual sensors and create kind of a heat map of where the pollution is, and then inform these workers to take measure? And yes, other domains as well, not only in an office. And last one, what are other uses for virtual sensors that we haven't really seen in the literature? Can we maybe inform ventilation systems operations to ensure the inhabitants' safety, like getting rid of the pollutants while minimizing the energy usage? And that was all. Thank you so much for your attention.